So by definition, I squared equals -1. But this means that when you have I to the fourth can be broken down into I squared times I squared. So when you multiply like bases, like I, you're going to add the exponents. 2 plus 2 is 4, so that makes sense. And then each I squared is just -1, so I squared is -1, I squared is -1, -1 times -1 is +1. So when you get to the fourth power of I, you get back to 1, which means that I to the fifth power is really just I to the fourth power times I. I to the fourth power we just showed is just 1. This goes away to just be 1. 1 times I is I. And that is what makes powers of I what's called cyclic. They go back through themselves over and over and over again. So I cubed is I squared times I. I squared is -1. I is just I. And that gives us -I. So I cubed is the same thing as -I. Here we can see that if we have I times I is I squared. I times I squared is just -1. So I times I is -1. Then we have I times I times I, which I just found here. I cubed is -I. -I is right here. So that just goes down here. And then I just showed you that I to the fourth power is 1. So I times I times I times I is +1. And again, I to the fifth power is the same thing as I. So we go back to here. This is what is meant by cyclic. It just goes through this behavior over and over and over again. And really, there's only 4 unique powers here. I to the 1 power, I squared, I to the 3 power, or the same thing as -I. And then I to the fourth power is the same thing as -1. So we can use that when evaluating larger powers. We're really asking how many times does I to the fourth power come out of this, because that'll make it a lot easier to work with. I to the fourth power is just 1. For 17, I can rewrite this as I to the fourth times 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 I. Right? Powers of exponents, if you multiply like bases, you add the exponents. 4 plus 4 is 8, plus 4 is 12, plus 4 is 16, plus 1 is 17. So this is the same thing. Each of these I to the fourth is, however, just 1. So we get 1 times 1 times 1 times 1 times I, which is just I. So I to the 17 is just this point here, which is I. We went around 4 times. 3, 4, and then we were right here, and we moved over 1 more. That's the idea that I want you to get here. Now, to do very large powers of this, all we have to do is do a division by 4. So we're asking how many times can 4 go into 1002 evenly? Well, if you take a calculator and go 1002 divided by 4, you're going to get 250.5. 250 means that it goes 250 times evenly. 4 times 250 is 1,000. So 4 can divide into 1,000, and that means that there's 2 left. So I can write this as this. I to the 1,000, which is really just a power of 4, times I squared. I to the fourth power to the 250. That's just a rule of exponents. 4 times 250 is 1,000. I just broke it up. And I to the fourth power is just 1. 1 to any power is 1. So 1 to the 250 is 1 times I squared is just I squared. And I squared is -1. So I to the 1002 is the same thing as I squared, which is just -1. Now, interestingly, we can actually go backwards and have negative powers. Now, negative powers, we could, of course, write this as 1 over I cubed, and then use complex division to simplify. You can also think of this in a different way. If multiplying by I just moved forward, then negative powers moves the other way. So we're going to start at 1 because this is the same thing as 1 times I cubed. Multiply it by negative 1, so we put us here. Sorry, an I to the negative 1 power. I to a negative 1 power puts us here. And I to 1 more negative 1 power puts us right here. So this is actually the same thing as I. I can show that a different way by doing, I'm going to multiply by I, because this gives us I over I to the 4th power. And I to the 4th power is 1. Well, I over 1 is just I. And that's the same thing. So I've solved it 2 different ways, one geometric and one algebraic. But both ways give me the same answer. Give it a try in number 4. Okay, so when we have I, we can work with radicals, with negatives of radicals underneath the square root and write them in complex form, which then allows us to do more things with them. We're not limited to saying, well, we can't solve it because it's a negative underneath the square root. There is one issue with that, and that is that order matters in how you simplify a radical. So I'm going to solve this the same expression 2 different ways, and it should be the same answer, but you're going to find out that it's not. The first way I'm going to do it is I'm going to use the rule of radicals that says you can combine 2 radicals that are multiplying under 1 square root. And of course, negative 9 times negative 4 is 36. The square root of 36 is 6. Okay, now I'm going to solve this a different way. I'm going to first rewrite the radical as a complex number. This is the same thing as saying the square root of 9 times negative 1. 9 is just 9 times negative 1. The same thing is true for negative 4. It's going to be 4 times negative 1. I can break up the radical over multiplication. So we have the square root of 9 times the square root of negative 1 times the square root of 4 times the square root of negative 1. The square root of 9 is 3. And the square root of negative 1, this is I, right? I squared equals negative 1, which means I equals the square root of negative 1. So this is just I. The square root of 4 is 2, and the square root of negative 1 is I again. Here we have 3 times I times 2 times I. That's going to give us 6 times I squared. I squared is negative 1. 6 times negative 1, which gives us negative 6. So we get both positive 6 and negative 6 when we do it 2 different ways. They should be the same answer, but they're not. So one of them has to be correct. And the correct method is the second one. Whenever you're simplifying radicals, take out the negative first. And this process I did here, I was just showing you why we can do this, but really it's a lot easier. If I had the square root of negative 9, I can rewrite this by just taking the negative out as an I. So it becomes the square root of 9i. So that's always the first thing you're going to do. Do not do this method. It will always be incorrect. Okay, let's give it a try with more complex problems. So we have square roots here. I'm going to first take out the I first. 3 root 50i plus 2 root 40i minus 10 root 75. Now I can simplify the radicals down. 50 is 25 times 2. 25 does have a perfect square in it. So we're going to write it as the square root of 25 times the square root of 2i plus 40 is 4 times 10. 4 has a perfect square in it. So 4 times 10 I minus, once again, 75 has 25 in it, so I want to write it like that. The square root of 25 times 3. Okay, so now the square root of 25 is 5. The square root of 4 is 2. The square root of 25 is 5. Root 2i plus 4 root 10i minus 50 root 3. And there is no like term here. We can't combine anything. I can, however, write this in standard form. That would be like this. I just take the I out of that so that we have one term there with the I on the outside. But this is probably better off using a calculator to simplify it down. But you can see the first thing I did is I took the negative out. I took the negative out as an I, and then I simplified down. Okay, for this next one, we know what x is, so we're going to plug x into there. So we have I plus 1 squared plus 6 over 6 minus x, which is I plus 1. Now I'm going to simplify this statement down. I plus 1 squared is going to be I plus 1 times I plus 1. Factor that out. We're going to get I squared plus I plus 1. Or this is negative 1. Negative 1 minus, or negative 1 plus 1 is 0. I plus I is 2i. So this is actually just 2i. On bottom, I can distribute the negative. So I get 2i plus 6 over 6 minus I minus 1. 6 plus 2i, that's the standard form on top. On bottom, I can combine like terms. I get 5 minus I. And we don't like this division. It needs to be in a better form. So we're going to multiply by the conjugate. On top, we get 30 plus 6i plus 10i plus 2i squared. On bottom, this is multiplying complex conjugates, so we're going to get 25 minus plus 5i minus 5i minus I squared. Okay, combining like terms, this is the same thing as negative 2 because I squared is negative 1. Negative 1 times positive 2 is negative 2. 30 minus 2 is 28. 6 plus 10 is 16. On bottom, the i's cancel. This is the same thing as negative 1, so negative of negative 1 is positive 1. 25 plus 1 is 26. I can simplify everything by 2, and that's it. I'm going to also break up the fraction. So we're going to get 14 over 13 plus 8 over 13i. And that is in standard complex form. So that's going to be my final answer there. Okay, give it a try in number 5. Now, complex numbers, as I've shown, are two-dimensional, and because of that, they have many applications, as functions also have many applications, or graphs in general. They're two-dimensional. So they use complex numbers in electricity, and talking about its flow, they actually use that to show the two-dimensional nature of electricity. It's also used in dynamical systems. Dynamical systems is the main term that's used that encompasses a thing called mathematical chaos. So very basic idea is to use the iterative expression. This is how we're going to build the Mandelbrot set. The iterative expression z squared plus c. So z is going to start as 0, and c we're going to set to some complex number that we choose. In this case, let's just choose 1 plus I. So the iterative expression means that we're going to plug 0 into here and calculate with our desired c value. So z squared plus c. Z is just 0. C becomes 1 plus I. That's going to give us 0 plus 1 plus I, which is just 1 plus I. This becomes the new z value. However, c will always remain at 1 plus I. Okay, let's do it again. So this is what was meant by iterative. You do it again and again and again. So our new z value, so z squared is going to be 1 plus I squared plus c. C is still 1 plus I. That's going to give us 1 plus I is 1 plus I times 1 plus I. So 1 plus I plus I plus I squared, which is, this is -1. Those cancel. We get 2I. So we get 2I plus 1 plus I, or 1 plus 3I. And this becomes the new z value. So plug it in again. Z becomes 1 plus 3I squared. Then C is still 1 plus I. We still haven't changed that from the very beginning. 1 plus 3I, 1 plus 3I, 1 plus 3I plus 3I plus 9I squared. That's going to be -9 plus 1. It's going to be -8 plus 6I. So we have -8 plus 6I. That's this first portion here. Then plus 1 plus I. -7 plus 7I. That would become the new z value. And you plug it in again, and so on. It continues on indefinitely. And this thing will actually get bigger and bigger and bigger. Well, actually, the complex number will become bigger so that you actually graph it farther away from the origin. And this number itself, how this works, will go off to infinity. Now, the only values of c that result in z squared plus c not going to infinity are in the Mandelbrot set. So this value would not be in the Mandelbrot set. So some values of z blow up to infinity very fast. For instance, if I plug in like a c value of 100 plus 100i, this would go to infinity very, very quickly. How the iterative expression works. Others, like the one we just chose, was a little bit slower than this one, and you can have even slower ones than that. Sometimes, however, you can plug in numbers that will bounce around forever, and some will just go to 0. It all depends on which number you choose. If we color code this how fast it goes to infinity or it goes to 0, that's what gives us the Mandelbrot set, which is this picture right here. Now, along the black border, along this border here, is where the mathematical chaos happens. Everything on the outside here, all the colored stuff, goes off to infinity. This set is called a fractal, and that it's got this self-similarity if you're to zoom in portions of it. For instance, if you zoom in right here, you're going to see almost the exact same image right there if you just zoom in on it. Also, if you zoom in right here and a bunch of other places where you zoom in. The number we chose, 1 plus I, how the complex plane works, I believe it goes like this. And this is the real axis here. This is the imaginary. This is 1. And then up here would be I. So 1 plus I is right here. And you can see that's way far outside of the Mandelbrot set. That goes off to infinity pretty quickly.